So in this video we're going to compare fractions, and comparing fractions really means seeing which one is bigger than the other, or whether or not they're equal. In other words, they're the same or equivalent. Okay, so let's start with some problems that we might want to tackle. Let's just write down compare, let's see, something like 5/7 and 2/3. 5/7 and 2/3. And this is an example where you might be able to immediately tell which is bigger than the other, or whether they're the same, equivalent. But when we get into larger fractions, it's very difficult to see, and even with this example, it's almost impossible to judge it. So it becomes a problem that we've got to solve. Now, what I'm going to do is just put up the number line here, zoom in, so that we can see exactly what we're dealing with before actually solving the problem. Okay, so what are we saying? We're saying 5/7 and 2/3. Where exactly are they on the number line in comparison to each other? Let's start with the 2/3 because that's easiest for us to sketch out here. So what I'm going to do is just divide this unit here into 3. So if I say, well, 1/3 is about there, and then half of that will give us our other division, and then we can say, well, here we've got 1/3, so that's where that lies, and here we've got 2/3. All right, now 5/7. Well, 5/7 is a bit trickier. I'm going to have to guess 1/7 is about, let's say, about there. And then if I divide this into 6, well, I can then halve it, and then we'll go about here and about here. Oops, about here, there and there. That looks, yeah, it's a bit uneven. Let's just move this one here, move that down a little bit. But I think that's a reasonable sketch for us to get at least a first position on this comparison. So we've got 1/7 then, 2/7, 3/7, 4/7, and here's our 5/7. So by the looks of it, by our sketch here, 2/3 is less than 5/7. And so we can use, let's just write it down here, we can use our greater than and less than symbols to express this. So our guess is, and that's all it is at the moment, our guess is that 5/7 is greater than 2/3. Okay? But how would we set about proving it? Well, various ways of doing it, but I think one good way is called cross multiplication. So cross multiplication is when we look at the denominator here and the denominator here and say, well, if I multiplied this side by what we've got here, in other words, multiplied this by 3, and if on this side I multiply everything by 7, we won't alter the fractions, but we will get the same denominator, so we'll be able to compare them. Okay, so we'll have, in this case, 20/1. Okay, so what we're going to do then is rewrite this. So let's just use this symbol here and say 3 times 5 on the top there over 3 times 7 we think is greater than 7 times 2 over 7 times 3. And we've got to work this out, and that should prove whether this symbol is right or not. Okay, so that will then give us 15 over 21, which hopefully is greater than, yeah, we've got 14 over 21. In other words, and we can write this i.e. 5/7 is not only greater than 2/3, we can say the difference between 5/7 and 2/3 So 5/7 subtract 2/3 is going to be greater than 0. Okay, in other words, it's not going to, if I subtract this one from this one, we're still going to get a small number here, small fraction. In fact, it's going to be 1/21st. But it's going to be positive. It's going to be greater than 0. So we've completed our first one. Let's call this A. Let's call that A. And let's do something else. Let's call that B. Okay. So let's think. B can be, yeah, let's have something like this. So we got 10/14 and 15/21. Let's stick with those 21sts because that's quite a nice number to work with. Okay, so that's our second problem. Compare 10/14 and 15/21. All right. Well, again, we could have a look at the number line, but before we do that, I hope we can see that these are fractions that we can simplify. So we can rewrite 10/14. That can become 2 times 5, and this is 2 times 7. Okay, now we've got 2 times 5 and 2 times 7. We can cancel the 2's, so that just becomes 5/7. Let's see if we can do the same then with 15/21, 15 divided by 21. So, well, yes, both divide by 3, so we can say 15/21 equals 3 times 5 divided by 3 times 7. Cancel those 3's then, and we've got 5/7. In other words, we've got the same as we had with 10/14, so we do have equivalent fractions here, i.e. 10/14 equals 5/7. Let's get the original fraction that we need to 15/21. Okay, 15/21. So those are called equivalent fractions. Let's just write that in brackets. And that's a term that you should know. Equivalent just means equal values. So equal. Okay, let's try something else. Now, what we'll go for here are top-heavy or improper fractions, as we should call them. So 7/3 and let's say 12/5. What we want to do when we're generating these numbers is we want things that are, as close as possible to each other, if not equal, so that it's a problem that we want to solve. Okay, so these are pretty close. Pretty tricky to see what the answer is here, which is bigger than the other. Are they equivalent? We could do it on the number line, so let's go back to our number line here. So we've worked out that there's 1/3 here, 2/3 here. In other words, 1 is 3/3. So we could write that like that. 3 divided by 3 is 1. Let's put our divisions in. Now we're going to have 4/3, whoops, and then 5/3 and 6/3 to get us up to here. Now we need to divide this one up. So here we've got our 7/3. Okay. Right, what about our fifths? Well, I'm just going to, I think, just erase that top line there then, because we don't want sevenths anymore, we want fifths. And we can immediately say, let's get rid of that dot there, we can immediately say that this one here is going to be 5/5, so 1 is 5/5, 5 divided by 5 is 1. Here then would be 10 divided by 5, 10/5 is 2. Now we can divide this one up. Let's guess that a fifth is about here. Divide that in half, divide it in half again, and that looks about right. So we've got 11 fifths, 12 fifths is here then. So if we mark that and mark this, it looks as though, let's write it like this as a hypothesis, that 7/3 is this time less than 12 fifths. So just using the number line, we've come up with a hypothesis. We now need to prove it. We need to demonstrate that 7/3 is definitely less than 12 fifths. It looks as though it is, but can we be sure? Okay, well, we can use cross multiplication again. So that would give us 5 times 7, and this one would give us, so we want the bottom to be the same, so 5 times on the bottom as well, 5 times 3. So 5 times 7 divided by 5 times 3 is the same as 7/3, and that should be, we hope, less than, so we're going to do 3 times 12 divided by 3 times 5. So we haven't done anything clever here. We've just multiplied top and bottom. If we multiply top and bottom, what we're doing is we're doing the same to the top as the bottom. We're multiplying that up, and same with this. Okay? So, sort of the reverse of simplifying, I guess you could say, whereas here we went down on both sides, here we're going up. Okay, so then we can say we've got 35 fifteenths, which hopefully is less than 36 fifteenths, and that we can see immediately is correct. In other words, 7/3 subtract 12 fifths is less than 0. It's going to be a negative value. All right, one final challenge then. Let's this time introduce percentages. Now percentages, let's say something like 33%, are sort of fractions in disguise. You could say they're special kinds of fractions. 33% is simply 33 divided by 100. So percent means divide by 100. And let's say something really as close as possible. Okay, sorry, and 67ths would be a good one to use, and we'll have 23/67ths. Okay, so 33% and 23/67ths. So let's write that down here. Well, let's start with that percent though before we go any further. So 33% we said is 33 divided by 100. And what I can immediately do, what this suggests, is another kind of method instead of cross multiplying this time, because our cross multiplying is going to be really quite tricky. I think we're going to have 67 times 33. So I'm going to try a different method here. Let's have a look at decimals. So one thing we could do is just divide 33 by 100, and that will give us our decimal of 0.33. Okay, so that's our first number that we want to deal with, and I can't estimate with this one. I can't really use the number line, so I'm not going to use that because I'd have to divide it up in such tiny figures. It's not going to be accurate at all. So I'm just going to work with these decimals to see if I can compare them in that way. So 33 divided by 100 is 0.33. Okay, let's just try the other fraction that we've got. So we've got 23 divided by 67. So we're going to use long division here. So we put our 67 as our dividend, our 23 here. Not giving ourselves much room, but hopefully it'll be okay. So to get a decimal, what I'm using is a long division method, and then I'm going to put my decimal point here and some zeros here. Let's just use 2 zeros, and we can add some more if we need them. Okay, everything's lined up. We're ready to do our division, and immediately we're going to say, well, 23 into 67, 67 divided by wait, I've done it the wrong way around, haven't I? Made a mistake. So mistakes are good. So not a problem. As long as we spot our mistakes, then we're fine. So what I'm going to do here is just change this around. So it's actually 23. Very easy to do this. 23 divided by 67. So our divisor goes to the left because we're using a left to right method. Okay, so there was a mistake. Not a problem. Easy to spot because we were going to end up with a whole number, and or a number larger than 1. What we realise we've got is a fraction. So 23 divided by 67. Okay, so now we're going to say that 67 into 23. Well, that will give us a 0 to start with. So there's no 1s here. It's going to be less than 1. So we're going into our tenths. So we're now saying 67 into 230 tenths. Well, we're going to chunk this up then. Let's say 3 times 67 looks like a likely figure. 2 times 67 I can see is going to be far too small. 3 times 67 is going to be the same as 3 times 70. Subtract 9. So that's going to be 200, and 3 times 70 is 210, subtract 9 is 201. Okay, and that sounds about right. So we've got 201 here. And if you're not sure, always go to the side to do those calculations. I did that quickly mentally, but do go to one side if you're worried at all about things like that. You could even just do 67 plus 67 plus 67, just chunk it up that way if that's easier for you. Okay, so now we've got 230 subtract 201, and we've got then 29. Bring down our 0. So we're now into the hundredths, but we know we've got 3 in the tenths column. Okay? Now, we don't have to go much further because all we need to prove is that one is greater than the other. And so if this is 3, then it's going to be greater. In fact, I think it's going to be 4. If we think of 67, add 67 is 134. So 67 add 67 equals 134. Let's just put our equals here. That was 201, wasn't it? Yeah. So 134 is if we have 2 times. If we have 4 times, that's going to be 268. So let's write that down, 268, giving us a 4. So even if it had been 3 times 67, it would have been greater than this, because it would be 0.33 dot something something something. But here it's definitely bigger because it's 0.34 something something something. So this is going to go on. But we don't need to go on because we can see that immediately that we've proved that this is bigger than this. And so we can immediately say, i.e. 33 over 100, or 33%, same thing, is less than, okay, 23 over 67. These were the original figures that we were given. Or we could say again, we could rewrite that, i.e. 33, or let's just put therefore would be better in this case. So therefore, let's just erase those. Therefore, 33 33%, to give us, to go straight back to here, 33% subtract 23/67 is going to be less than 0. Okay, so I hope that's helpful. It's important now, of course, for you to try practice some of these techniques for yourselves and look at different comparisons. So I suggest just taking some numbers for yourself, writing them down and seeing if you can prove that the one fraction is bigger than or less than the other, or that they're equivalent. Right, so let's just look at cross multiplication and how that works, because it's obviously a useful method. But before we do that, I just want to say a few things about the kind of numbers we're dealing with when we're talking about fractions. So in earlier videos we talked about the natural numbers, which are denoted by an n. Let's just make that clearer, so an n like that. And the natural numbers, as we know, are the counting numbers. They start at 1 and they go up and on forever, but they only include whole numbers, not fractions. Now, the natural numbers then are incorporated into the set of integers, the z numbers, and these of course include 0. They also stretch to infinity in the negative direction, and then we get the natural numbers going on. Going on again, tending towards infinity. Now, what we can see from this is that, again, that there are no fractions included in the set of integers. So what we're going to need is a new set of numbers that include not only the integers but also the fractions, if you like, the in-betweens. So we call these the Q numbers, denoted by a Q symbol like that. And we can no longer list them out because there are far too many of them. We know they've got the integers, so the negatives, the 0 and the positives, but we've also got these other numbers like 2/3, 7/9, 8/3, and so on and so on. So far too many to list out. We can, though, as we've seen, represent them on the number line if we stop thinking of the number line as just being made up of whole numbers. Now I'll show you what I mean. If we put a 0 here and we go 1, 2, 3, these are the negatives, and we go 1, 2, 3 going in the positive direction. Up to now, when we've just been talking about integers, we've had to jump on our number line. So 0, 1, 2, 3. Now what we're doing is saying, well, actually, rather than this being discrete places, so like things, we can divide our number line up, ideally almost anywhere. So if we divided it between the 1 and the 2 here, for example, somewhere along here, we're going to have another value which we can represent by, well, let's say 7/4. Okay, so 7/4. And what we've done is we've taken two of our integers, divided one into the other to give us this in-between value that we call a fraction. So that's our definition of a fraction, really, is that it's one number. We can say it algebraically. It's one number, let's say n, divided by another number where m and n are both integers. They're whole numbers, but also they might be negative whole numbers. Either way, we get a fraction. Okay, so that's what a fraction means. That's what a fraction is. It's somewhere along this continuum of the number line. It can actually be on one of these points, as we've seen. So -2, for example, -2 could easily be expressed as -4 divided by 2. So it could be expressed as a fraction as well. But what we've done, and the important thing that we've done, is that we've expanded our natural numbers to get integers. Now we're expanding our integers to get rational numbers. Okay, now what about this idea of cross multiplication? Cross multiplication. So let's say we had something like, let's have another one, let's say just 2/3 here. So that would be 1/3. Okay, so it's that bit there and that bit there. So we should say, let's do this properly. Let's say 1/3 here and another third here, and that gives us 2/3. So we've defined our 2/3 here, and so let's write it over here, 2/3, and let's choose another one. Let's have 8/12. Okay, so we've got, well, let's just write them out. So we've got 12th here, 12th here, 12th here, and a 12th here. How many have we got there? 4. So 4 more. And so that's that length there. So we've got 8/12 compared with 2/3, and we can immediately see, even if we hadn't already spotted it, that these are equivalent because they measure out the same length. Okay, well, we could also prove it numerically, which is what we were doing, using the cross multiplication method. And all we did with the cross multiplication method is we said, let's just prove that 2/3 equals 8/12 by multiplying this side by this denominator here. So 2 times 12. And if we do one thing to the top, to the numerator, as we call it with fractions, we have to do the same to the denominator. So we got 3 times 12 as well, giving us 24. Oops, 24 at the top and 36 at the bottom. We do the same to this side, but this time we take that 3 and we say 3 times 8 and 3 times 12. So again, we've got 24, 36. In other words, what we've done is we've converted both of these to things that are the same. Instead of trying to compare thirds and twelfths, which are different, obviously, twelfths is much smaller than thirds, what we've done is found a method that allows us to have the same thing to compare. So we've got 36ths in this case and 36ths on both sides. So once we've done our calculation, we could see they were exactly the same. What's going on here? Well, we've algebraically got 4 different numbers, so we can say the 2 can be represented by A, any number, B, another number, equals C divided by D. So if A divided by B equals C divided by C, the cross multiplication method is when we take this number, but it could have been any number really, and multiply both top and bottom. In other words, what we're doing is we're increasing, as long as that's a positive, we're increasing both the top and the bottom. That means we end up with A times D. I'll just do a dot for the multiplication symbol. We're doing A times D and B times D here. So we've taken our D, we've multiplied both the top and bottom. We haven't altered A divided by B because those D's would simply cancel. Okay, but that's what we did. And now on the other side, we just took that B and we said B times the C on the top and B times the D on the bottom. Now you can see why this works, because if we're taking those two numbers, we could have taken any number, but if we're taking those two numbers and multiplying, then we're going to end up with the denominator being exactly the same. And that's why the cross multiplication method works. Now, in a later video, we'll question that. Cross multiplication isn't always the best way of working. And here's a good example of that, in fact, not being the best way of thinking about this. If, for example, we were to change this to a subtraction, let's swap them around and say 8/12 subtract 2/3, then I don't think we'd really want to go up into 36. We can simply increase this one and this one so that we can express that as 8/12 subtract, well, if we multiply by 4, we've got 2 times 4, and then 3 times 4, we end up with 8/12 subtract 8/12 equals 0. So we don't have to cross multiply. We don't have to go into such a large division here. We can keep it simpler, and we call this finding the lowest common multiple. So in a separate video, we'll look at finding the lowest common multiple and see how that applies to fractions. But for the moment, hopefully that was helpful.